Okay, so this is problem 20. Comes from chapter 4, the problems and exercises section. So problem 20, it reads, suppose a 60 kilogram gymnast climbs a rope. A, what is the tension in the rope if they climb at a constant speed? So what's the tension in the rope if they climb at a constant speed? B, what is the tension in the rope if they accelerate upward at a rate of 1.5 meters a second squared? Okay, so first off, let's see what we're given. Let's write out what we're given. And we're just given that this gymnast, their mass is 60 kilograms. Okay, so let's look at part A. So in part A, they ask us this: what is the tension in the rope if they climb at a constant speed? Okay, so a constant speed, that's given to us. And so a constant speed, what does that imply? Well, that means that this change in velocity, that's going to be equal to 0 because it's constant, it's the same. So the initial is the same as the final. Okay, when we deal with a change in velocity, anything that deals with a change in velocity, such as like an acceleration, because remember, our acceleration is this change in velocity over change in time. And then if it's just 0 over our change in time, then our acceleration is just 0. So we have that. We know that our gymnast isn't providing any type of extra force onto our system. So we can draw a free body diagram. If we have this gymnast, it's just going to be a ball. And they're climbing up a rope. So this is the rope. So it's just a ball climbing up a rope, basically, to put it very simple. And let's identify our forces. We know that there's some weight associated because there's a mass. They tell us a mass, and this weight is just going to be equal to mg. And then we know that with some rope, if we pull this rope, if it doesn't break, there's going to be some type of tension to it. And it operates in this direction here. So we know that this force, rather, I guess since there's no external force acting on our object, we have this equation: F net is equal to this force minus this force, because it's in the opposite direction, is equal to 0. Why is it equal to 0? Well, remember, we know that in Newton's second law, so I won't draw it here, but Newton's second law states that the mass times the acceleration. So this is Newton's second law. Law of second Newton's. So we have this. Then all we have to do, remember, acceleration 0, so this is 0. So ma, the net external force, is equal to 0. So that's how we get 0 on the other side. If we wanted to determine the tension, we can just move it on the other side, and it's just this weight, which is mg, which is just this 60 kilograms times 9.80 meters per second squared. And if we do the math, this comes out to be 588 newtons. So this is it for part A. This is the tension in the rope for part A. And then let's have part B. Part B says that now they're moving with a constant, or with this acceleration. So now there is an acceleration. So we can use these same equations. But now F net is equal to T minus this weight, which is equal to M times A. A is not 0 anymore. They say A is this 1.20 meters per second squared. So it's pretty straightforward. Same diagram. It's just now they're moving. And we'll see this tension is going to be MA plus the weight, which is 60 kilograms, times the acceleration that's being given here, times this acceleration that's given here. So this acceleration is this 1.20 meters per second squared, plus the weight. And we know what the weight is. The weight, remember, it's the same magnitude as the here as the tension, so 588 newtons. And so when we do our math, we'll see that this just comes out to be 660 newtons. So just remember the main important part here, we were given in part A that there was a constant speed, which means that acceleration was 0, which gave us this relationship here regarding Newton's law. Then in part B, there was an acceleration. So now we had this equation for Newton's law instead of this equation down here, where we had to incorporate this acceleration. So 588 newtons for the first part, and then 660 newtons for the second part. And that's it.